Okay, so what we're going to be doing today, as we mentioned previously, is we're going to just do a recap on the quantitative aspects of chemical change. So it's not going to be quite long. We just want to go through it. We want to recap it again. Probably was done before lockdown, as the students have already advised me. But I think it's worth going through a bit of a recap because this does take us all the way through to grade 12. It gets more intense as we get to grade 11. Most of the intensity happens in grade 11. So if we recap it now, it won't be so bad. Okay, so let's just zoom in a little bit. Okay, cool. It's a little brief introduction here. Okay, that shows us a reaction here in the Siabula textbook for grade 10 physical sciences. In this little introduction, it gives us a reaction there that happens between iron and sulfide, or sulfur rather. So we end up with iron sulfide, which is FeS. Alright? Okay, so now that's a perfectly balanced equation. We can see everything works out fine. They bond with each other. The substance exists. But what we don't see here in the reaction, what we don't see is that from just looking at that equation or that reaction, we can't see the quantities or the amounts of each substance that is involved in this reaction. We can't tell the amount of iron that reacted with the amount of sulfur. Okay, just by looking at that equation. Okay, so the mole and atomic mass will help us. Okay, it will help us determine the quantities or the amount of a substance that is involved in different types of reactions. Okay, so we will know how much sulfur is needed to react with iron. Right? We will know how much sulfur or how much iron is needed to react with sulfur so that all of iron is used up and that there's no excess iron around. So the atomic mass of a substance and the mole of a substance do help us determine that. Okay, so this chapter does aim to quantify, okay, the changes that do take place in chemical reactions. Okay, so that's the overview of the chapter and the overview of what we're going to have a look at first, which is atomic mass and the mole. Okay, cool. So the first aspect is the mole. Now the mole does not disappear, the mole stays. The mole will stay with us all the way up until grade 12 and if we move on to university physics. Okay, and boy, they'll tell you that university physics is quite fun in the first year. By that I mean people fail. But they fail not because they are being challenged or they're stupid or they don't know their physics, but that's how a little tricky and complicated it does become. Okay? That's how tricky and complicated it does become. So what we're going to do is we're going to focus, we're going to learn the mole here in grade 10, so when we get to grade 11, we know we can just build upon it. So we're going to lay that foundation for it right now. So, the textbook does say sometimes. Okay? In fact, it's almost all the time important to know. Okay? Because often when you get to a lab, you don't just throw substances together. You might just blow yourself, the lab, or if not the whole country up. Alright? If you work at a nuclear power plant, you need to know exactly what you were doing. Hey, there was an explosion at the oil refinery not so long ago. Luckily, with just people injured and not dead, and they managed to get on top of the situation and get that situation under control. If they had not been able to do that, oh my word, we might all be dead. Right? Everybody around the Century City Canal Walk area would all have been dead. Okay, that's why we must be very careful, and that's why we must know the amount of substances that we are just chucking together when we are doing any type of experiment to achieve a reaction. But we'll go over what the textbook says. Sometimes it's important to know exactly how many particles, for example atoms or molecules, are in a sample of a substance. Okay? or what quantity of a substance is needed for a chemical reaction to take place. Up until now, we've not taken that into consideration up until this chapter. The amount of substance is so important in chemistry, it is given its own name, and that's why we have the heading there called the mole. Okay, the mole, by definition, alright, on the next page, okay, is the amount of a substance. That's all it is. It's the amount of a substance. Very short definition. Okay, it's abbreviated to mole, M-O-L. Alright, mole. You don't want to say mole, you want to say mole. Okay, that's its SI unit. Okay, standard international unit. Which means over here it's the same, over there it's the same, everywhere it's the same. Okay, and it's for the amount of a substance. Okay, like I've mentioned in my introduction before, you can't just chuck things together. Okay, you need to know exactly how many particles are here, what's happening, because maybe too many particles could result in a lethal reaction that could be very detrimental, reaction that could actually kill you as the experimenter, right? So you must know. If you're given a mass of a substance, it's important to know, okay, I've got 800 grams of a certain substance. That doesn't tell me the amount, just tells me its mass, right? I need to know the amount in mole of the substance. And that's where the atomic mass comes in. But first we're going to have a look at this other little wally called Avogadro's number. Okay, so let's find out what Avogadro had to say about the mole. Now, Avogadro's number, that is a constant number, okay? And basically Avogadro took the mole and basically, I wouldn't say modified it, but basically his number dictates the amount of particles that are in 1 mole of a substance, okay? So we define the mole as a unit, okay? It's a counting unit, okay? Just like hours or days, okay? Or minutes or months. It's a counting unit, okay? The reason why they've made a reference to hours or days, because we can count 1 second, we can count 1 hour, we can also count one minute, we can count 1 month. So the mole's the same thing. If you want bigger units of time, like just sticking with the time reference, then we refer to, like I've mentioned, days, months, or years. Okay. Even longer periods of time, what do we know? We convert to them in centuries, millennia. All right, which is a millennium. All right, millennium is 1,000 years. Millennium meaning thousands, 2,000s. Right? If you want to say for thousands of years, you can say for millennia. But of English lesson, right? Physics is everywhere. Now the mole is bigger than even millennia, just more than 1,000 years. Right? Mole's bigger. Okay. They're telling us that 1 mole is made up of, and here's Avogadro's number, 6,022 times 10 to the power of 23 particles. Alright? That's weight, like, hey, I can count, hey, I don't have a counting problem, but this is quite a huge number. Alright? This is quite a huge number. I'm not even going to attempt. That's why we have a scientific notation, so I don't reinvent the wheel. I'm just going to take it as 6,022 times 10 to the power of 23 particles. Okay? That's Avogadro. Okay? So by definition, Avogadro's number is telling me that in 1 mole of a substance, there is about 6,022 times 10 to the power of 23 particles of any substance. Okay? Of any substance. Doesn't matter which substance it is. Avogadro's number is always going to be that. Always going to be that many particles in 1 mole. Do I have any questions so far? Alright, I'm just checking what I see here.
JP?
Talk to me.
So a mole, 1 mole would be basically the amount of a substance, but how does the Avogadro number, does that like specify the exact number of that substance?
So Avogadro's number doesn't specify the exact amount necessarily. That's the mole, right? But Avogadro's number is telling me that in 1 mole of a substance, because now if I've worked out how many mole of a substance I have, right? Let's say that substance, that mole is 3 mole. Okay, 3. So I have 3 moles of, let's pick a magnesium. Now the next question, Alex, is calculate how many particles are in the mole that you just calculated in the previous question. How many particles are within the substance, right? And that's where Avogadro's number comes in. So if you've got 3 and 1 mole is equal to 6,02 times 10 to the power 23 particles, then 3 mole must be 3 times that. Are you with me?
Yeah.
Did I answer your question?
Yes, you did. Thank you.
Okay, awesome. Cool. So how do we use Avogadro's number? So we use Avogadro's number and the mole that's within chemistry to help us quantify what happens in a reaction. Okay? So the mole is a very special number to every chemist, right? Physicist, chemist, right? That love chemistry. It's a very special number. So in the example here, if we measure 12 grams of carbon, right? So 12 grams of carbon, alright, we have 1 mole, or 6,22 times 10 to the power of 23 carbon atoms. Now let's take note of that quickly, ladies and gentlemen. That basically, we know that 1 mole, alright, the number of particles in a mole is equal to 6,022 times 10 to the power 23 particles. Take note, we know that, okay? Now they tell us, if we measure 12 grams of carbon, alright, 12 grams of carbon is the same as 1 mole, which is the same as 6,022 times 10 to the power of 23 carbon atoms. Only if I have 12 grams of carbon do I have 1 mole of carbon, basically. Alright? If I look at the next one, if I have 63,5 grams of copper, that is 1 mole, or 6,022 times 10 to the power 23 copper atoms. So if we measure relative atomic mass of any element on the periodic table, we have 1 mole of that element. So let's go have a look quickly on the periodic table. So on the periodic table that we have here, they said, let's zoom in a bit, that we have 12 grams of carbon, right, as we see there. The atomic mass, alright, which we see here, we have the element, carbon, atomic mass, bottom, electron negativity on the top, and the number on the left. So this is a key for this periodic table, saying that the number of the elements, so you see hydrogen's the first element, and the second element is helium, and the third one is lithium, the fourth one is beryllium, boron, and the sixth one is carbon. Alright, its atomic mass of this element is present underneath. So 12 grams of carbon, as we see here, means that I have 1 mole of carbon. Aluminium, I have 27 grams of aluminium. That means 27 grams of aluminium means I have 1 mole, or 6,022 times 10 to the power of 23 aluminium particles, or atoms, guys. Same thing here if we have oxygen. Oxygen, relative atomic mass over here we have is 16. So if I have 16 grams of oxygen, that means I have 1 mole of oxygen, which means I have 6,022 times 10 to the power of 23 particles. So that does confirm this last sentence here, that if we measure the relative atomic mass of any element on the periodic table, we have 1 mole of that element. Sorry, I dropped my pen. We have 1 mole of that element. Okay? So if we go to this little short exercise here, okay, I'm not going to do entirely, I just want to pick up something quickly. How many atoms are there in 1 mole of a substance? Well, this is easy. First one is easy, right? Because in 1 mole of a substance, according to this definition here, we've got 6,22 times 10 to the power of 23 in 1 mole of a substance. Great. So 1 mole of a substance, I should have 6,022 times 10 to the power of 23 particles or atoms. And if I have 2 moles of calcium, well, that should be this number times 2. 5 moles of phosphorus, that number times 5. And so on and so forth. So the molar mass now is different. The molar mass is capital M. First of all, that's how it's denoted in formula. The formula, which we'll see a little later on, is capital M. Alright? Now, molar mass is the mass of 1 mole of a chemical substance. Alright? It's the mass of 1 mole of a chemical substance. Okay? We know now how many particles is 1 mole of a substance, but now we want to know the mass of that substance of 1 mole. Okay? The unit for molar mass is grams per mole, or G dot mole to the negative 1. Okay, and I'll explain that in just a moment. How it comes to the grams per mole to the negative 1 thing, I'll explain it all now again. So basically, your molar mass is the same as your atomic mass almost. Okay? It's basically the same thing. Okay? So you find that on your periodic table. Okay? So exactly what I just explained here, the textbook also explains in more words. So when it comes to mass in grams of a specific element, okay, you know that that element is equal to the relative atomic mass, okay, because the relative atomic mass is a sample that contains 1 mole of that element. So if I have 12 grams of carbon, I know that I have 1 mole of carbon. Okay, if I have 12, okay, grams of carbon, that means I've got 1 mole of carbon. 24 means I got 2. Okay, 36, I know I've got 3 moles of carbon. Okay, so if my atomic mass and my relative atomic mass basically means that that is the sample of 1 mole, then when I get to a molar mass of a specific element, it's equal to exactly the atomic mass of that element. Okay, so if I have 2 moles, then I know that the molar mass, if I have 2 moles of carbon, then the molar mass is going to be equal to 24. Right? If I have 2 moles of oxygen, then I know the molar mass is going to be equal to 32. Right? And that's how it goes. And we'll see it more clearly in an example. But what I want to do quickly, I just want to explain this whole grams per mole quickly and why it's to the negative 1, even if people may or may not know. But let's just assume that there are people that don't know, and this might just help them. So we know it's measured in grams per mole. Okay, that's all well and good, but whenever we see per, alright, and other examples we have kilometers per hour. Okay, that's how we say it, in kilometers per hour. And we all know that kilometers per hour is written most commonly like this. Okay, now we see that little line here. This basically indicates a fraction. Okay, I've got a numerator and a denominator. Okay, kilometers per hour basically looks like if you wrote it as is not a hybrid fraction like this, but an actual fraction that we all know how to write in mathematics. It will be written like this: kilometers per hour. Okay, so this is where the laws of exponents comes in. So I've got kilometer to the power of 1. I've got h to the power of 1. Hours to the power of 1, but power of 1 at the bottom here is only to the power of 1 when it is on the bottom, because it's division. Kilometers per hour, kilometers divided by the hour. Okay? So if I bring it up and I want to change that nature, So I want to write it all in one line. It's going to be kilometers, which is the power of 1, times hour to the negative 1, because I've brought it up to the numerator. The same thing over here. Grams per mole basically means grams divided by the mole, which basically, if you want to write it in one straight line, it's grams times mole to the negative 1, because that means that that is on the bottom here. Okay, same thing here. Hope everybody gets that little analogy. Alright, so what's good to remember when it comes to a relative atomic mass as well as molar mass, okay, is that it can be interpreted in two ways. Okay, first way, and how we have defined it, is that the mass in grams of a single average atom of that element relative to the mass of an atom of carbon. Okay, because remember, carbon 12, or 12 grams of carbon means 12 grams of carbon means that there's 1 mole of that substance. Okay, so when we say relative, we're always comparing it to. Okay, so in other words, the mass of a single average atom of that element, we are basically comparing that to the mass of an atom of carbon. Okay, or we can look at it as the average atomic mass of all the isotopes of that element. Okay, isotopes you will see as you get to the trick. Isotopes does come more into theory and into learning. Okay, but what isotopes means is that it looks the same, but it's not exactly the same. It's almost like a hybrid. All right, and we'll focus on that when we get to organic chemistry in grade 12. Okay, but the third one, and definitely the third one, is how we look at it differently in grade 10 and 11. Is that the relative atomic mass means that that is the mass of 1 mole of the element. Alright? And this way is how we determine or use the molar mass of that element. So I would say, to avoid confusion, to avoid a lot of questions, always think of the relative atomic mass as number 3. Relative atomic mass is the mass of 1 mole of the element. Alright? Which basically, this third use is the molar mass of the element, because the third one, number 3, doesn't go away in grade 11, it doesn't go away in grade 12. So number 3, if you look at the relative atomic mass, it means that that is the mass of 1 mole of that element. Focus on 3, forget 1 and 2. 1 will be learned next year, and 2 will be learned closely in more detail in grade 12. Okay. And this table does quantify, alright, magnify what I just said about the third way that we can, that we view the relative atomic mass. For example, if you look at the element of magnesium, or one that I haven't looked at in a long time, let's look at lithium. Okay, lithium, alright, relative atomic mass, sometimes denoted by the letter U, right, its symbol, letter U. If you look on the periodic table, it will have a relative atomic mass of 6,94, which is the same as the molar mass, grams per mole, of lithium, and which is the same as the mass of 1 mole of this element. Alright, in grams, 6,94. Right? So your relative atomic mass is your molar mass, which is the same as mass of 1 mole of that element. It stays the same. So going through just an example here, which is a textbook worked example. So I like these textbooks. They do go through worked examples, so they basically provide you with the foundation. You know, a lot of textbooks don't have the worked examples as explicitly outlined as Avogadro does, so that's why I like using them for our classes. Alright, so this example here, for example 1, is just calculating the number of moles from mass. Okay, so now they say calculate the number of moles of iron, which is Fe, in an 11,7 gram sample. Okay, so step 1 is that you first got to find what is the molar mass of iron. Alright, so that, as they tell us, if we look at the periodic table, Alright, so let's actually go have a look at the periodic table, okay, which I know is on page 2 of this textbook. Okay, so if I go to find iron, which is Fe, somewhere around here, not usually it's in the middle somewhere. My eyes are jumping. So what I'm gonna do, if my eyes jump, I need to just stop, and I found it. Cool. So if you look on periodic table, we see for Fe, for iron, you can see that the molar mass is 55,8. Alright? 55,8 grams per mole. Okay, we've established that. Let's go back here. Here we are, 251, sorry. This means that 1 mole of iron has a mass of 55,8. Okay, now they tell us that we need to now find what is the mass of iron. So if 1 mole of iron has a mass of 55 grams, then the number of moles of iron and I see that in this example here, they cocked up, made a mistake with the numbering. They said 11.7 grams, and I see it was actually supposed to be 111.7. Okay, unfortunately, some of these textbooks do have a little bit of errors that they didn't revise. So it's fine. We pick it up because we are good students. So we picked it up. So it actually should have been 111.7. So if you want to find out now how many moles is in 111.7 grams, we take 111.7 divided by 55, and we get the number of moles, which is 2 moles. Alright, so if 1 mole is 55.8, then 2 moles must be 111.7 grams. Alright, so we just found out the number of moles from after we were given a mass sample. Okay, fortunately, sorry about that in the question. I didn't do it. Question it was 11.7, but it should have actually been 111. If it was 11.7, it still would have been okay. Could have still said 11.7. Not like it's a problem. It still said 11.7 divided by 55.8. We wouldn't have gotten 2 though. I would have gotten an answer which is about 0.2. It's about 0.21 moles of iron in that substance, right? Or in that sample of iron. 11.7, about 0.21. But I see they actually meant for it to be 111.7, so 2 more. The equation to calculate moles as well as mass. Okay. If you look at it in a triangular pyramid formula, okay, the number of moles of a substance, okay, is equal to the mass of that substance in grams divided by the molar mass, which is in grams per mole. So N is equal to little m divided by big M. That's how I remembered the formula. That's how I taught the formula to myself when doing all these calculations. When I was at school, I did a truckload of calculations when I was at school with this formula. N is equal to little m over big M. When I would write it, I would hear those words in my head. N is equal to little m over big M. Alright? So, another way, this is also how you can rearrange your formula if you see it in a triangle. So this also means that the molar mass is equal to, if I want to calculate the molar mass of a substance according to this formula, that should be equal to the mass in grams divided by the number of moles. Alright? And the mass of a substance, if I try to work out the mass of a substance, I should take the number of moles of that substance, multiply it by the molar mass of that substance. Alright, so this little triangle is a pyramid of formula is great for remembering. It shows you how you can rearrange things and how the formula is formed. Okay, with this form. Okay, so this is the formula for the mole, the standard formula for the mole, which you'll see all the way up and you'll use up until matric, is N, which is the number of moles, alright, is equal to the mass of that substance, little m, divided by the molar mass of that substance, big M. So let's have a look at an example where we're calculating the moles from mass. So if I calculate the number of moles of copper that there are in a sample, that with a mass of 127 grams. And let's hope this question is correct. Okay? So what are they asking me to do? They're asking me to calculate the number of moles. So I first write down the equation. N is equal to mass divided by the molar mass. Number of moles is equal to the mass divided by the molar mass. N is equal to little m over big M. Now I've already been given the mass. I've been given little m. And they've mentioned the substance to me. It is copper. Alright? So I go to my periodic table and I find out what is the molar mass of copper. And if I check on the periodic table, and I'm going to check on my one over here in my hard copy textbook. Alright? It's just another textbook over there, physics textbook. Copper, which is Cu, is 63,5 grams. And molar mass is 65, 60, did I say 65? No, it's supposed to be 63. Yeah, sorry, 63,5 grams per mole. And I have the grams, which is 127. So 127 divided by 63,5 gives me 2 mole, which means that in actual fact there are 2 moles of copper in the sample. And I worked that out all from this formula over here. Let's take it a step further. In example 4. Now they say calculate the number of atoms there are in a sample of aluminium with a mass of 87 grams. Okay? So solution is first we need to find the number of moles. So we can't find the number of atoms without knowing first what is the number of moles. And the way we find the number of moles is by calculating it from the formula N is equal to little m over big M. When we do that, okay, we have 81 grams for M, the mass, we sub in. It's aluminium on the periodic table, it's 27 grams per mole. 81 divided by 27 gives us 3 mole. So we have 3 mole of aluminium here. Now we've answered the first half of the question. The next half of the question, which obviously is the main question, is the number of atoms. So now, if there are 3 moles, that means the number of atoms is equal to 3 moles times Avogadro's number, which is 6,022 times 10 to the power of 23. If we do that, we get an answer of 1,8069 times 10 to the power of 24 aluminium atoms in a sample of 81 grams of aluminium. And guys, that is the basics of almost the basics of grade 10 when it comes to quantitative aspects of chemical change with regards to looking at the mole and looking at the molar mass. You see, it's quite simple. Alright, it's quite basic, it's not that difficult. Okay, we just want to take you through one more aspect when it comes to looking at compounds of certain elements. So for example here, it comes to a compound with H2SO4, okay, and they ask for the molar mass now of a compound. It means we need to add up the molar mass of every single element here. So we know hydrogen has a molar mass of 1,01. We know sulfur has 32,1 grams per mole. That's its molar mass, and oxygen is 16 grams per mole. So if we work out for the entire compound, we need to add them all up. So I have 2 hydrogens, so 2 times 1,01. And I have 1 sulfur, so just plus 32,1. And I have 4 oxygens, so plus 16 times 4. So hence the molar mass of the entire compound of sulfuric acid is 98.12 grams per mole. So that wraps up this week's lesson. Thank you all so much for joining me on this first revision section on mole. And we will tune in next week for the second session. We will just revise a little bit more, and then we will be done with this topic.